Now we are going to discuss about Orifice meter. Orifice meter is the device which is used to measure the flow rate in case of pipes. Orifice meter working on the principle of Bernoulli's equation and continuity equation. Orifice meter is less costly as compared with the Venturi meter. Venturi meter is also very reliable flow measuring device. There are some pressure losses in Venturi meter and it is used in large volume liquids and gases. Venturi meter is expensive due to complexity of its design. In case of Venturi meter, we have one is convergent part, throat and divergent part. So the construction of this Venturi meter is difficult. Therefore, Venturi meter is expensive due to complexity of the design. Therefore, in order to determine the flow rate in small pipes, generally use the Orifice meters for the determination of flow rate in case of small pipes. Right? And also Orifice meter is better. This is about the difference between the Orifice meter and Venturi meter. Okay? Once again I am going to repeat it. Orifice meter is the device which is used to measure the flow rate in case of pipes. The Orifice meter is working on the principle of Bernoulli's equation and continuity equation. Orifice meter consists of one flat circular plate and this circular plate will have one circular sharp edge. The circular sharp edge hole is termed as orifice. This is the pipe. This is orifice. This is the circular orifice. This circular sharp edged hole is known as orifice. Right? The diameter of the orifice is 0.5 times the diameter of the pipe. And also the diameter of the orifice varies 0.4 times the dia to 0.8 times dia. The diameter of the orifice is varies from 0.5 to 0.8 times diameter of the pipe. Right. Orifice will restrict the flow of fluid and will reduce the cross-sectional area of the flow passage. Because this is the orifice provided here, because of this, the cross-sectional area of the flow reduces. This is the cross-sectional area of the flow reduces. This is the pipe diameter. This is the cross-sectional area reduces because of the provision of the orifice. Right? A difference pressure will be developed across the orifice plate. This is the here. Difference pressure head will be developed across the orifice plate due to creation of pressure difference. Now, types of orifices. Orifices are basically classified as, these are the ways. One is eccentric orifice plate, sharp edge orifice plate, segmental orifice plate, and conical orifice plate. Now we are going to discuss about sharp edge orifice plate. Derivation of rate of flow through orifice meter. Right. Let us consider one horizontal pipe. Let us consider one orifice meter fitted in the horizontal pipe. This is the horizontal pipe. Here provided one orifice meter here, and the water is flowing through the horizontal pipe. Right. Let us consider two sections. This is section 1 and this is section let us consider two sections, that is over the pipe. This is section 1 and another section is this is the section 22. One section is upstream side of the orifice and another section is downstream side of the orifice. One end of the differential manometer is connected at section 11. One end of the differential manometer is connected at section 22. The differential manometer upstream side of the orifice is, that is 1.5 to 2 times the dia of the pipe. The distance between the orifice and differential manometer on the upstream side of the orifice is 1.5 to 2 times the dia of the pipe. Whereas the differential manometer connected to the section 22, or the distance between the section 22 and the orifice is 0.5 times the dia of the pipe. Okay, this is 0.5 times the dia of the pipe. This is 2 to 1.5 to 1.5 to 2 times the dia of the pipe. Right, this is about orifice meter. This is section 11, this is section 22. Right, here P1 is the pressure intensity at section 11 and V1 is the velocity at section 11. D1 is the diameter at section 11. P1 is the pressure intensity at section 11. V1 is the velocity at section 11. A1 is the cross-sectional area at section 11. And at section 22, D2, P2 and V2 and A2 are the corresponding values of section 22. That means D2 is the diameter at section 22. P2 is the pressure intensity at section 22, V2 is the velocity of flow at section 22, and A2 is the cross-sectional area at section 22. Now, once again recall what is the Bernoulli's equation and what is the continuity equation. If the flow is ideal, incompressible, and the flow is steady and continuous, the pressure head plus velocity head plus datum head at one section is equal to the pressure head plus velocity head plus datum head at the another section. Okay. Now, this is section 11. This is section 11. This is section 22. Pressure head means P1 by W plus V1 square by 2G plus Z1 at section 11 is equal to section 22. P2 by W plus V2 square by 2G plus Z2. This is the Bernoulli's equation. Based on the Bernoulli's equation, sum of the pressure head plus velocity head plus datum head at one section must be equal to pressure head plus velocity head plus datum head at the another section. The assumptions used in the Bernoulli's equation, same assumptions are applicable here also. Therefore, the assumptions used in this derivation of the discharge from the orifice is fluid is ideal, inviscous and incompressible. That is the first assumption. And second one, fluid flow is steady and continue. And fluid flow is irrotational and frictionless inner surface. These are the assumptions used in the derivation of the discharge from the orifice meter. Apply Bernoulli's equation at section 11 and section 22. Right. Now, this is the diagram. In this diagram, the orifice meter is provided. This is section 11. This is section 22. The orifice meter is provided here. This is orifice meter is provided downstream of the section 11 and upstream of the section 22. Right? Now, what is the Bernoulli's equation? Right. Pressure head, velocity head, datum head at section 11. What is the pressure head at section 11? That is equal to P1 by W plus V1 square by 2G plus Z1 is equal to, at section 22, pressure head plus velocity head plus datum head. Pressure head at section 22 equal to P2 by W plus V2 square by 2G plus Z2. Okay, this is the Bernoulli's equation at section 11 and section 22. Now, this equation can be written as P1 by W plus Z1 minus P2 by W plus Z2 is equal to V2 square by 2G minus V1 square by 2G. Right? This is move this side, and this one also moving towards this side. This V1 square by 2G is moving towards this side. Therefore, P1 by W plus Z1 minus P2 by W plus Z2 is equal to V2 square by 2G minus V1 square by 2G. The pressure difference between section 11 and section 22 is pressure difference between section 11 and section 22 H is equal to P1 by W plus Z1 minus P2 by W plus Z2. This is the equation already I have explained earlier class, in the last class. Right? H is equal to P1 by W plus Z1 minus P2 by W plus Z2. That is the pressure at section 11, pressure head plus datum head at section 11 minus pressure head plus datum head at section 22. That is the pressure difference between the section 11 and section 22. Therefore, in place of here, in this equation, P1 by W plus Z1 minus P2 by W plus Z2, in place of this we are going to take H. Therefore, H is equal to, that is the pressure difference between section 11 and section 22 is equal to V1 square by 2G, V2 square by 2G minus V1 square by 2G. Right, this is equal to V2 square minus V1 square divided by 2G H. This is equal to 2GH is equal to V2 square minus V1 square. From this equation, 2GH is equal to V2 square minus V1 square. Then V2 square is equal to 2GH minus V1 square. This is the relation between the V1 and V2. V2 square is equal to 2GH minus V1 square. This is the equation we have in the earlier slide. That is equal to V2 square is equal to 2GH plus V1 square. Here we are going to observe one point. That is, at section 11, the diameter is D1. At section 22, diameter is D2. But here, the orifice is not provided at section 11 or section 22. That is just beyond the section 22. This is the orifice. Because of the orifice, here cross-sectional area reduces. Cross-sectional area gradually reduces here and increases here. Cross-sectional area reduces and increases here. We have taken section 22 at the reduced cross-sectional area, that is at the Vienna contract. This point is also known as section 22 is taken at the Vienna contract. But now the dia of the orifice is more than the dia of the Vienna contract. Okay. Already I have explained coefficient of contraction is equal to area of the Vienna contract divided by area of the pipe. That means coefficient of contraction is equal to area of the Vienna contract divided by area of the pipe. Right. Therefore, here dia at the Vienna contract is equal to D2. Dia of the orifice is equal to D0. Dia of the orifice is equal to D0. Dia of the Vienna contract is equal to D2. That means that is section 22. Okay. Or area at the orifice is equal to A0. Area at Vienna contract is equal to A2. Okay, therefore coefficient of contraction is equal to coefficient of contraction cc equal to area at vena contract divided by area of the pipe, that is area of the orifice. Here area of the vena contract means area at section 22, area of the pipe means area at orifice. From this equation A2 is equal to coefficient of contraction into A0. This is very important relation. Cross sectional area at section 22 is equal to coefficient of contraction into cross sectional area of the orifice. Cross sectional area of the orifice. Right. Apply continuity equation. We want to determine what is the value V1 in terms of V2. We want to determine what is the value V1 in terms of V2. That's why we are going to apply here continuity equation. What is the continuity equation? A1 V1 is equal to A2 V2. That means cross sectional area at section 11 into velocity at section 11 is equal to cross sectional area at section 22 into velocity at section 22. Right, A1 V1 is equal to A1 V1 is equal to A2 V2. Right, from this equation V1 is equal to A2 V2 divided by A1. Okay, A2 V2 divided by A1. This is equal to, already we have derived A2 is equal to Cc into A0. In place of A2 we are going to take this value. Right, therefore Cc into A0 into V2, right, divided by A1. V1 is equal to Cc into A0 into V2 divided by A1. Cc into A0 is nothing but A2. Right, A2 is equal to Cc into A0. Now in place of V1, this is the standard equation already we have derived. In place of V1 we are going to take this value. Right, therefore V2 square is equal to 2gh plus, in place of V1, what is the V1? V1 is equal to Cc into A0 into V2 divided by A1 square. This is square. Right, and V2 square is equal to 2gh plus Cc square A0 square V2 square divided by A1 square. This is the relation we have. Right, V2 is equal to 2gh plus coefficient of contraction square into area of the orifice square into velocity at section 22 square, area at section 11 square. Right, what is the equation we have? V2 square is equal to 2gh plus C0 square into A0 square into V2 divided by A1 square, and this is equal to 2gh plus A0 square A1 square into C0 square into V2 square. Okay, this is equal to 2gh plus A0 by A1 square into C0 square into V2 square. Now this is nothing but V2 square. V2 square is equal to, this is the equation. From this equation we have 2gh is equal to V2 square minus A0 by A1 square into C0 square into V2 square. From this equation 2gh is equal to V2 square minus A0 by A1 square into C0 square into C2 square. Now we are going to take V2 constant in this equation. Therefore, 2GH is equal to V2 square taken out 1 minus A0 by A1 square into C0 square. 2GH is equal to V2 square taken out from this equation 1 A0 by A1 square into C0 square. Therefore, from this equation V2 square is equal to 2GH divided by 1 minus A0 minus A1 square into C0 square. Right, this is the equation we have. V2 square is equal to 2GH divided by 1 minus A0 by A1 whole square into C0 square. Right, this is the equation we have. Last class we have, this is the relation V2 square is equal to square root of V2 square is equal to root 2GH divided by 1 minus A0 square by A1 square into CC square. From this equation, V2 is equal to square root of 2GH divided by 1 minus A0 by A1 square root into CC square. Now we want to determine the rate of flow through the orifice meter. Therefore, rate of flow formula we know, that is Q is equal to AV, or Q is equal to A1 V1 is equal to A2 V2. Right, here we have the value V2. Therefore, Q is equal to A2 V2. Now already we have the value determined for A2. Area, cross-sectional area at section 2 is equal to cross-sectional area of the orifice into coefficient of contraction. Right, now we are going to substitute this value here, divided by A1. A1 is nothing but, this is the value, this is equal to A0 into CC into V2. V2 value, this is the V2 value, root 2GH divided by square root of 1 minus A0 divided by A1 square into CC square. This is the relation we have. Discharge Q is equal to A2 V2. In place of A2 we have taken A0 into CC. That already we have derived in the last slide. In place of V2 we have taken this value. For the determination of discharge Q is equal, this is the relation. I have given one more relation, that is coefficient of discharge and coefficient of contraction. That relation I have given where we have discussed about hydraulic constants. The relation is coefficient of discharge is equal to coefficient of contraction into root 1 minus A0 divided by A1 square divided by square root of 1 minus A0 divided by A1 square into CC square, coefficient of contraction square. From this equation, now coefficient of contraction CC is equal to CD into square root of 1 minus A0 by A1 square into CC square, 1 minus A0 by A1 square into CC square, square root, divided by 1 minus A0 by A1 square, square root. Now, in place of CC, we are going to substitute the value in the above equation. That is, this is the value we have. CC is equal to CD into root 1 minus A0 by A1 square into CC square divided by square root of 1 minus A0 by A1 whole square. Right? Now we are going to substitute the value in the standard equation. That standard equation is equal to, standard equation Q is equal to A0 CC root 2gh divided by square root of 1 minus a0 by a1 square into cc square. Now in place of cc, already we have derived one equation, that value substitute here. Therefore q is equal to a0 into cd into square root of 1 minus a0 by a1 square into cc square into, right, first we are going to substitute cc value divided by square root of 1 minus a0 by a1 square into root 2gh divided by square root of 1 minus a0 divided by a1 square into cc square. Right, 1 minus a0 by a1 square into cc square root, and this value cancel. Therefore q is equal to a0 into cd into root 2gh divided by square root of 1 minus a0 divided by a1 square. Right, this is equal to a0 into cd into root 2gh divided by, this can be written as square root of a1 square minus a0 square divided by a1 square. This is from this equation we have square root of a1 square minus a0 square divided by a1 square. Therefore discharge q is equal to a0 into cd into root 2gh into root a1 square divided by square root of a1 square minus a0 square. Now this cancel. Therefore discharge q is equal to a0 into cd into root 2gh into a1 divided by square root of a1 square minus a0 square. Right, this is the formula for the determination of discharge from the orifice meter. That means q is equal to a0 a1 square root of 2gh divided by square root of a1 square minus a0 square. This is the formula for the determination of discharge from the orifice meter. Right, now this is, and also into cd. Therefore q is equal to cd into a0 a1 square root of 2gh divided by square root of a1 square minus a2 square. This is the formula for the determination of discharge. Here cd is the coefficient of discharge of orifice meter. This value is less than 1, and also the coefficient of discharge of orifice meter value is much smaller than the coefficient of discharge of the venturi meter. The coefficient of discharge of orifice meter value is quite smaller than the coefficient of discharge of venturi meter. Right, this is about orifice meter. What is Pitot tube? What is the purpose of the Pitot tube? Pitot tube is defined as the device which is used to measure the velocity of flow at any point in a pipe or the open channel. Pitot tube is the device which is used to measure the velocity of flow at any point in a channel or in the pipe. Pitot tube is working on the principle of Bernoulli's equation. What is the Bernoulli's equation? The pressure head plus velocity head plus datum head at one section must be equal to pressure head plus velocity head plus datum head at the another section. Based on this statement, at one section pressure head decreases, automatically velocity head increases. Okay, at another section velocity head decreases, automatically pressure head increases. The sum of the total pressure head plus velocity head datum head at one section must be equal to the another section. Right, this is the Pitot tube. This is the bent glass tube inserted in the channel. This is the Pitot tube. Suppose this is section 1-1, this is section 2-2. At section 1-1, having some velocity head and pressure head. At section 2-2, that velocity head is converted into pressure head. Because of this Pitot tube, here this velocity head default that converted into pressure head. But the sum of the pressure head plus velocity head plus datum head at section 2-2 must be same. Just that velocity head converted into pressure head only, right? We are going to discuss some more points related to the Pitot tube. Pitot tube will be made of glass tube bent at a right angle as displayed here in the following figure. Right. Pitot tube is made up of glass tube bent at 90 degrees. Second point, the lower end of the Pitot tube, this is the lower end of the Pitot tube, this is Pitot tube. The lower end of the Pitot tube will be bent at right angle and will be directed in the upstream direction. The lower end of the Pitot tube is bent at right angle. Now, at this point, the conversion of kinetic energy into pressure energy, right? Due to conversion of kinetic energy into pressure energy, liquid will rise in the glass tube. Because of this Pitot tube provided here, the kinetic energy at this point is converted into pressure energy. Therefore, the liquid is raised in the glass tube. This is the actual level of the liquid, but that is raised at a height of small h. Because the kinetic energy at this point is converted into pressure energy. Derivation of velocity of flow through Pitot tube. Derivation of velocity of flow through Pitot tube. Now, this is one open channel or pipe flow. So, this is the Pitot tube provided here. The center line of the Pitot tube and the top level, the water level is capital H. Right? Once because of the provision of the Pitot tube here, the kinetic energy is converted into pressure energy. Therefore, the rise of water in the glass tube like this, the depth is small h. Now, we are going to take section 1-1 and section 2-2. That is, this is section 1-1. This is section 2-2. At section 1-1, P1 is the intensity of pressure, V1 is the velocity of flow, and A1 is the cross-sectional area. At section 1-1, there is no obstruction. The channel water, the channel having same parameters. The liquid flow with a velocity V, same velocity maintained here. The channel having velocity V1, same velocity maintained here. But at section 2-2, we are provided Pitot tube that the pressure is, intensity of pressure is P2, velocity is V2, and cross-sectional area is A2. Because of the provision of the Pitot tube, these values are changed from the section 1-1. And H is the depth of tube in the liquid, that is depth of tube in the liquid. And small h is the rise of liquid in the tube above the free surface. This is the free surface, this is the free surface. Right, above the free surface, the water raised in the tube is equal to small h. For the determination of velocity, here we are going to use the Bernoulli's equation. Once we are going to recall what is Bernoulli's equation. Bernoulli's equation is derived from the Euler's equation of motion. And this Bernoulli's equation is derived based on the assumptions that the fluid is incompressible and ideal, fluid is a steady flow and continuously flowing. That are the basic assumptions. Based on that assumptions, we have derived the Bernoulli's equation, so that here also same assumptions are applicable. Right? First assumption, fluid is ideal and inviscous, incompressible. Fluid flow is steady and continuous. Fluid flow is irrotational. Frictionless inner surfaces. These are the assumptions used in the derivation of the velocity of flow through the Pitot tube. Right? we are going to apply the Bernoulli's equation at section 11 and section 22. This is section 11. This is section 22. Bernoulli's equation, you know, pressure head plus velocity head plus datum head. P1 by rho g is the pressure head at section 11. V1 square by 2g is the velocity head section 11. Z1 is the datum head at section 11. Corresponding values, P2 by rho g plus V2 square by 2g plus Z2 is the pressure head plus velocity head plus datum head at section 22. Right, the datum head is same because this is the horizontal. In section 11 and section 22, datum head is same. Therefore, Z1 is equal to Z2. And another point, pressure head at section 11. What is the pressure head at section 11? This is the section 11. If there is no obstruction, the pressure head is H. The pressure head is H. That means P1 by rho g is equal to H. Next one. What is the velocity head? Same velocity head at section 11. There is no obstruction. There is no change in the velocity or pressure. Right? Therefore, V1 square by 2g is equal to V1 square by 2g. And another one, Z1 is equal to Z2 is equal to Z. Right? This is nothing but Z1 is equal to Z. Right. Now, go to section 22. Section 22. What is the velocity at section 22? So, having velocity V, because of this Pitot tube, that kinetic energy, that velocity head is converted into pressure energy or pressure head. Therefore, the velocity head at section 22 is equal to 0. That is, V2 square by 2g is equal to 0. Right. Another one, this is equal to 0. Another one. So, here the velocity head is converted into the pressure head. Therefore, the pressure head at section 22 is equal to, what is the pressure head at section 22? Already have some pressure head, that is H. Because of this kinetic energy is converted into pressure energy. Because of the pressure energy, the water level raised in the glass tube, that is equal to H. Therefore, pressure head at section 22 is equal to small h plus capital H. Okay. Therefore, P2 by W, that is P2 by W or P2 by rho g, pressure head at section 22 is equal to small h plus capital H. And another one, Z2 is equal to Z. Now, we are going to substitute these values in the main equation. Therefore, P1 by rho g is equal to H. P1 by rho g is equal to H. V1 square by 2g. P1 by rho g plus V1 square by 2g. V1 square by 2g is equal to V1 square by 2g plus Z1. Z1 is equal to Z is equal to pressure head P2 by rho g is equal to H plus capital H plus velocity head V2 square by 2g is equal to 0 plus Z2 is equal to Z. Right? Now, Z gets cancelled. H cancel. Therefore, V1 square by 2g is equal to small h. V1 square by 2g is equal to small h. Okay. V1 square by 2g is equal to small h, or V1 square is equal to 2gh, or V1 is equal to root 2gh. This is the velocity. Velocity in the channel or pipe flow is determined by using this equation. V1 is equal to square root of 2gh. But here, our assumption that the fluid is incompressible, ideal, steady flow. So that this determined velocity V1 is equal to root 2gh is the theoretical velocity. This velocity is nothing but theoretical velocity. theoretical velocity. Therefore, this is V theoretical is equal to root 2gh. But the actual velocity is less than the theoretical velocity. Therefore, the actual velocity is equal to some constant, that is the Pitot tube constant into theoretical velocity. We have the actual velocity. Therefore, velocity actual is equal to V actual is equal to CV into root 2gh, where CV is the coefficient of Pitot tube. The coefficient of Pitot tube value CV is always less than 1. Therefore, the coefficient, the actual discharge, actual velocity is equal to CV into root 2gh. Right.